So we talk about BigO exercise here. Okay, so what's BigO again? To measure the efficiency of your code, we use BigO. And BigO look at the worst case scenarios, right? So if you remember, we can create these expressions according from the code, live code, right? So like for example, if I look at this one, number 5 here. We see that when we code, we initialize count equals to 1, j equal to 0. And initialize I equals to count, pretty much now count pretty much equals to I, which is 1. And 1 less than the size of the n. N is the size, right? Of how many numbers, right, on the list. Or how many records. I keep increment, right? So it's going to be n for the loop, correct? Because I is depending on the size of n. If n is 100, so it's going to loop 100 times. So this is going to cause 100 loops. Right, initialize here is going to be 2, right, plus 2. So that's why we start to have plus like that. And what happens when it gets into a loop is also increment j. Right. So j equal to 0. Pretty much j plus 1. So pretty much just increment j, this statement, right? So let's review the BigO notation a little bit, right? So we have BigO of 1, that's represent constant. BigO of log n, that's called logarithmics. BigO of log n c, polylogarithmics. N, which is linear, right? N squared quadratics. N to the c, polynomial. C to n we call exponential, which is very slow, right? And this is we were talking about BigO. We look at less than equal, so the upper boundary, right? Worst case, right? So this is just the one that we focus here. So BigO look at CPU time, memory usage, disk usage, and network usage, right? So it's going to measure the performance, how much time memory disk usage is actually used when a program is run. So depending on machine, compiler, and etc., right? As well as your code. Complexity, so it's going to measure the complexity, right? Performance complexity. How do the resource requirements of a program or algorithm scales? So what happens as the size of the program being solved gets larger? Okay. So complexity affects performance, but not the other way around. So this time required by a function procedure is proportional to the number of basic operations that it performs. So right, arithmetic operations, add, subtract, multiply, and so on. Like assignments too, right? Read operations, write operation, test like the logic, right? Comparisons. This is happen to be not Java, so that's why syntax is different. Okay. So some function procedure perform the same number of operations every time they are called. Right? For example, stack size in the stack implementation always returns the number of elements currently in the stack, or states that the stack is empty. Then we say that stack size takes constant time. So functions procedures may perform different number of operations depending on the value of a parameter. Like for example, bubble sort algorithms, the number of elements in the array determines the number of operations performed by the algorithms. This parameter is called the problem size, input size. So when we're trying to find the complexity of the function procedure algorithm program, we are not interested in the exact number of operations that are being performed. Instead, we are interested in the relation of the number of operations to the problem size, right? So that's why we're interested in the worst case, which is BigO, which is the maximum number of operations that might be performed for a given problem size. For example, inserting an element into an array, we have to move the current element and all the elements that come after it one place to the right in the array. So in the worst case, inserting at the beginning of the array, all of the elements in the array must be moved. We talk about order list, right? Order array. So therefore, in the worst case, the time for insertion is proportional to the number of elements in the array. And we say that the worst case time for the insertion is the linear, right? N, right? The linear time algorithm, if the problem size doubles, the number of operations also doubles. So BigO notations. When we talk about linear, we write BigO n, right? Quadratics time BigO n square, constant time BigO 1. So BigO expression do not have constants or low order terms. Because when n gets large enough, constant and low order term doesn't matter, right? Don't matter. So let's look at this expression. So this is saying that, okay, Tn is a function of big of Fn, right? For some constant c and for value of n greater than some value n0. So this function is depending on n here. Even you multiply the constants. So you see that Tn actually the complexity is depending on Fn. Right? So we're going to say that it's going to be Fn, which is big O of n. We not worry about the constancy, right? Right, so a problem of size n will be no worse than Fn. In practice, we want the smallest Fn, the least upper bound on the actual complexity. So if we have 3 times n squared plus 5, so we can see that this is going to be of big of n squared, right? So it's if we choose c equals to 4, n0 equals to 2, so we talk about, this is because for all values of n greater than 2, so 3 times n squared plus 5 less than equals to 4 times n squared. So we talk about this, right? C times Fn. Cn here. So you still seeing that this is still smaller than this, right? So Tn is not big of n because whether constant c and value n0 you choose, there's always a value of n greater than n0 such that 3 times n squared plus 5 greater than c times n. So if you look at the statements now, so how would you determine the complexity? We say the complexity is what? Time of each statements that we have, we're going to sum them up, right? So that's the total time, right? So if each statement is simple, only involve like basic operations, like assign, multiplying, then the time for each statement is constant, so it's going to be big of 1 for each statement. So if then else, so either block 1 will execute or block 2 will execute. The worst case time is the slower of the two possibilities. So we go look at the max, right, of time that it takes for block 1 or block 2. So if block 1 takes big of 1 and block 2 takes big of n, then this program will cost big of n. So for the loops, so this is for each right, I in 1 to n. So we're going to do sequence of statements and end the loop. The loop executes n times. So the sequence of statement also executes n times, right? So execute n times. We assume the statement are, so we have to look at the statements. So if it's a simple operation at, right, assignment, so it's going to be big of 1. The total time for the for loop is n because of the loop, n times big of 1, which going to give you bigger of n as an overall. For nested loops, so if we look at I in 1 to n and j in 1 to m, so this is going to be big of n times m. And if this sequence of statements is big of 1, so just big of 1, so it's going to be nm, right? Or if it's the same size, then n squared, which is in a common special case where the stopping condition of the inner loop is j less than n, right? J less than n instead of j less than m. Then it's going to be big of n squared. Now, if you call the function procedures or the methods, right? So the complexity of the statement includes the complexity of the function procedures or the method itself. So assume that you know that function procedure f takes constant time, which is big of 1, and g takes k, right? Which is linear, right? Time. Now, let's look at this program. For j in 1 to n loop, g, j. So how long will it take? So loop will take n. It's going to pass. So this is not a simple statement anymore. Not like a constant time. So it's a linear time too. So this is going to cost another k, right? Which is depend on j, which j is going to be to n, then it's n squared. So big of n squared, right? Alright, so that's how we calculate the BigO. So big of 1 is for the statement here and n for the loop. then overall it's going to give you BigO of 1 as the answers, right?